So this set of videos is going to be about section 2.4, exact equations. What we're going to do is we're going to look at a quick motivating example kind of showing how you could already use this method and why you might want to do it. And then we'll look at the steps to solve this type of equation. And after we have those steps, we'll work on some examples, including one of those physical problems that kind of switches up the notation on us. And then after that, we're going to talk about the problem of making an equation exact so that we can use this method. That part can be kind of difficult, so you might want to pay special attention to it. And then one thing that I'll warn you about is that this section does tend to have a lot of algebra and integration involved in it. So just sort of be really careful in your work, kind of like work down the line. Even though it'll take up a lot of space, you'll thank yourself for it later. So our first thing here is going to be talking about our motivation for exact equations. Okay, no, that's not what I wanted. Okay, so what I'm going to do is I'm going to think about a differential equation, dy dx equal to minus y over x. Now, hopefully, when you see that differential equation, you think to yourself, I already know how to solve that. That's a separable equation. I learned it already. I would go dy over y is equal to dx over x times a negative sign. And so if I integrate both those things, I get like natural log of y is equal to minus natural log of x plus a constant. And when I solve for y, I get y is equal to e to the minus natural log of x plus a constant is e to the natural log of 1 over x times e to a constant is just some different constant times, well, it's just 1 over x times some different constant. So I already know how to solve that differential equation. Instead of doing that, let's think about if there's a different way we could solve it. So instead of rearranging to have all the y's on one side and all the x's on the other, what I'm going to do is I'm going to try to separate the dy and the dx from each other. And then just sort of get rid of this fraction. So I'd have x dy is equal to minus y dx, or x dy plus y dx is equal to 0. The reason for doing that isn't really clear at this point, but it is something we could do. And then you could note that the differential of xy is the same as x dy plus y dx. Just kind of think about this using like a product rule. So if you want to take a differential of xy, you'd have I keep x the same and I take dy, or I keep y the same and I take dx. And that thing that's the same as what we had before would also be equal to 0. And then from here, you could go ahead and take an integral. And you could say, oh, actually, I'll do that on the next step. You can kind of say, okay, well, I'm going to have the integral of d of xy is just xy. And the integral of 0 is always a constant. So then I have y is a constant over x. So we got the same thing, y is equal to a constant over x. We just used a different method. And that's going to happen a lot in this class. We'll learn methods where you can kind of use one or the other in some situations. And what we're going to find with this particular method is that it can solve these separable type equations, but it can also solve a couple different types. So we will, got to give it a title. So what we're going to be doing is we will be working with something called exact differentials, which you're going to just represent as some function m, which can have either x or y in it, dx, plus some function n that can also have x or y in it, dy, equal to 0. And then what's important, what makes these exact, we must have the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And so real quick, let's talk about this equation that we worked with right here. Kind of try to put it in the same context. So x dy plus y dx. Oh no, I did something. There we go. So x dy plus y dx equal to 0. This x attached to the y was our n, and this y attached to the x was our m. So then dm dy was just d dy of y, which is 1. And our dn dx was just d dx of x, which is also 1. So the reason why we could use that method that I just described to solve our separable equation was because it was exact. Because we have that m can be a function of x and y and n can be a function of x and y, it's actually going to turn out that a lot more equations than are separable are going to be exact. But the special property does have to hold. And then to understand why the property matters, I'm going to ask you to kind of think back on Calc 3. So you would have learned about like mixed derivatives. So you would have learned that like df dxy should be equal to df dyx. So just think about m and n being connected to the derivatives of the same function or being differential forms of the same function. Corresponding to. These differential forms of the same function. So sort of m is related to the derivative of a function with respect to x, and n is related to the derivative of a function with respect to y. And you can kind of see that by like where they're connected. So the thing connected to the derivative of x, when you take the derivative of y, should be connected to the thing that's connected to the derivative of y when you take it with respect to x. That's kind of why we have this condition. And I'm going to go ahead and stop here and then write the steps to solve this type of problem in the next video because they are a little bit long.